Thanks to the Scheibel Scholarship and the committee that considered my work important for the Alaskan communities. Well, basically what brought me to Alaska is my interest in geodesy and ground motion, and I think that Alaska represents a great study ground for that.
Well, thank you, Alex, and thanks, Rod, for the introduction. Before I start, I want to acknowledge that this university is on the ancestral land of the Lower Tanana Dene people, whose stewardship makes it possible for us to do our work. We will be talking about GPS today, or GNSS. Alex is going to explain the difference to you in a little bit. And hopefully you'll get away with this, or away from this, knowing a lot more of the potential applications of this technology. To start out, though, I want to kind of capture the everyday application of this technology. I oftentimes find myself in this state of not having a drink and wanting to be with a coffee, as the title of the talk says. And commonly how we work through this, particularly if we are in foreign cities that we just landed on or driving through in our car, is we pull up a phone and we ask some mapping application for where we could find, say here, Alaska Coffee Roasting Company when we are at the GI. And that actually is not that far removed a question. When I arrived here in 2007, there wasn't any of that really happening yet. I needed to ask somebody for directions, and now we end up with this blue line, and GPS is coming in at the level of this bubble, right? The blue bubble with your car in it. As you're progressing through the route to your destination, your location gets remapped due to the little GPS receiver in your phone. So this is one application. The other piece that we promised in the abstract to this lecture is that GPS really is a Swiss Army knife, but I find it more Alaska appropriate to move to a Leatherman super tool here and kind of map out all of the, or most, not even all of the applications that a GPS has. So we're going up here, something like plate kinematics, plate tectonics, you all heard about that, how Earth's plates move with respect to each other, earthquakes are generated that way, et cetera, right? So we can measure that. That's millimeters to centimeters a year of motion that we can record. We can learn something about the total electron content of the ionosphere. We'll talk a little bit about meteorology today. Vegetation water content is going to come up, volcano cycle, earthquake cycle, groundwater dynamics, permafrost, all topics in the GI that are being studied, soil moisture, et cetera. And then down here, there's this whole part that, again, interfaces or connects the science with society, which is hazard early warning. And GNSS has started playing an important role in earthquake early warning applications, but also for volcanoes, tsunamis, and landslides. It's very applicable. Now, how is this all possible? It really is enabled through the system design that has satellites in space that send a signal to receivers on Earth. And Alex is going to tell you about how all of that works.
So our story starts up out in the space where navigation satellites orbit the Earth at about 22,000 kilometers. And these satellites are known to us as the GPS satellites. Now, at the ground, there's also a receiver which is trying to listen and capture information transmitted by these satellites. However, GPS is not alone. Well, there are also other systems that have a same common goal to precisely point us where we are at ground. And these are the Russian GLONASS, the European Galileo, and the Chinese Beidou system. And together they form the Global Navigation Satellite Systems, or in short, the GNSS. Therefore, saying today that we use GPS to reach point B, it's slightly incorrect. because in fact our new receivers, so the new phones, use more than just one system. Going back to our satellites, each one of them sends time information through a beam in one direction towards the receiver at the ground. Large part of this information is reached by the receiver along the quickest way, so in a straight line, while the remaining is reached by the receiver with bit of latency produced by the reflection of the surrounding obstacles at the ground. The time information is then used by the receiver to derive its location. Now, the basic principle behind GNSS positioning is that each receiver needs at least 4 satellites in reach to derive its location. To do so, the measured travel time is multiplied by the speed of light to determine the distance between each satellite and the receiver. Now, to better understand this, in the next slide, I will use some plane geometry. So let's first imagine that the receiver is not able to track any satellite. And in that case, it can be anywhere on the globe. If the receiver tracks only one satellite, it will be able to determine the distance r1, and therefore it can be located anywhere along this blue circle. Now, assuming that the receiver can track 2 satellites, then it can be located at one of the 2 points of intersection between the 2 circles, which indeed it's not ideal. Now, if the receiver tracks an additional satellite, the problem is solved, and the solution is at the intersection of the 3 circles in just one point. Now, bear with me that in order to be able to determine its location, the receiver has to correct for its clock drift. And this is because the receiver is equipped with a much more affordable clock compared to the clocks on board of satellites, which are atomic clocks. That's why the receiver needs basically a 4th satellite. Now, so far, so good. Before the signal makes it to us, it actually travels through the atmosphere. So along its way, it gets first slowed down by the interaction with the ionosphere, which is a highly charged layer. Then it gets slowed down again by the interaction with the troposphere, which is the region where the weather is formed. And lastly, it also gets slowed down by the interaction with the ground surface. Now, by the fact that the signal is interacting with all of these, we can infer more than just locations. In fact, scientists use the ionospheric signal delay to estimate the amount of electrons in the ionosphere. They can also build better weather forecast models based on the information captured from the troposphere. If the GNSS receiver at the ground moves and we track that, then we can also raise earthquake alarms. Or we can even look into get more information about active volcanoes. If the reflected signal at ground can be used, then we can also infer more about the sea level rise, or we could even derive the snow depth. Now, at this stage, you know a bit about the path GNSS signals take in order to reach the receiver, which is exactly what enables us to do more than just positioning. And in the following, Ronni will talk more about these kind of applications.
Thanks, Alex. And I will now walk you through the signal path from the satellite to the receiver, and along its signal path, we will discuss some of the applications that are enabled by the system design. So first, we start at the satellite, and the signal starts traversing the ionosphere. What we need to know for this is that the ionosphere is dispersive for radio waves. What that means is that we have on GNSS satellites actually 2 signals that are being sent. It's not just one, it's 2 at least. And that is the minimum design to make it functioning, which is because of that property of the ionosphere. So first we have L1, which just means link 1 at 1.5 gigahertz, and L2 at a lower frequency at 1.2 gigahertz. Now what happens when these radio waves traverse the ionosphere is that they propagate at different speeds because the ionosphere is dispersive for radio waves. What does that mean? It's like in areas where we have higher electron content, right, that is being generated by the sun's radiation interacting with the ionosphere and generating free electrons, the signal at the higher frequency is going to propagate through this faster than the signal at the lower frequency, which is going to get slowed down more. You can think of that very much like with as a prism would function with visible light minus the refraction part. So we have higher electron content. One signal arrives a little bit faster than the other one. This is what we call ionospheric delay. But we can now solve for this. If the only reason that this is getting slowed down is the higher electron content, we can figure out the difference in arrival time and solve for the electron content if the signals are being sent exactly at the same time, which is the case. So we can solve for this and perhaps map globally the free total electron content. And this is what these maps are showing, okay? Over here, we have a map of global average change from some background total electron content. It's a map from September 2008. It was recorded by low Earth orbiting satellites. And 2008 was a solar minimum. And what you can see here is, it's not very colorful. There's not a whole lot of activity, and that's what we want to take away from this. On this side, we see the same map for solar maximum of September 2013. And you can see there's a stark difference, right? Way more free electrons in the Arctic and Antarctic due to higher activity of the sun. The point is, though, that this is being generated by satellites that orbit the Earth at a lower altitude than the GPS satellites, so they can measure exactly using the principle that I just explained, the ionosphere content. So having explained the ionosphere, or what we can use the GPS or GNSS signals for to understand the ionosphere, we can move further down in the atmosphere to the troposphere. Right? This is broadly where weather is being generated, so perhaps that is of interest to us too. We're going back to this image that I showed earlier, and we're forgetting about the ionosphere now. We've made it through there, and now we have the troposphere only that our signals are interacting with. Fortunately, the troposphere is non-dispersive for radio waves. That means we can actually, what I showed earlier, that differential arrival between L1 and L2 is not going to be further affected by the troposphere. That's great, because then we can really only focus on the ionosphere effect. For the troposphere, this non-dispersive slowdown or delay for radio waves means they're getting refracted more if you have more water content, right? So the darker gray here, if I go back and forth, right, there's not very much water content, more water content, not very much more. So the rays get bent a little bit. And if you were to straighten them out, right, you've got to think about these being wave fronts, not actually beams that are coming down, right? So that means there's some delay that both signals experience just the same way, so they're both slowed down identically. Okay, and they're arriving at our receiver a little bit later. Now we can estimate that delay with models. Right? We can perhaps measure what the air pressure is at a receiver site, and from that figure out what the water column might be above us, and create models that then map this delay here between the original travel time and the one with more water vapor into actually assessing the water vapor in perhaps even near real time. And this is what's being done here. So these are two maps. I want you to focus first on this side. This is a forecast from NOAA for precipitable water vapor in millimeters. That's on a standard scale from 0 to 70 millimeters, right? A lot of water vapor is very dark and nothing is white. What that means is that in an atmospheric column above you, there is that many millimeters of liquid water sitting that could be generating rain. And these forecast models here show that the southeastern US, there's high precipitable water vapor. If you move along the east coast, there's a lot less, or there's kind of a gradient. It gets less, right, down to 20 millimeters from maybe 40. And then you move into the central US, near high plains, it's kind of dry there. Towards the west coast, California is all dry. And you move up along the west coast. It gets a little bit wetter into Alaska, where we have some precipitable water too. Now on this side, a company that's called GPS Solutions generates these in real time. I think every 15 minutes or so. This is a map retrieved on February 17th at 1900 using about 1,000 GPS stations to estimate, with these models that we just talked about, what the precipitable water content could be. And you can see that the colors reflect very much the pattern that we see in the forecast, right? A lot in the southeastern US, less as we move towards the north, almost nothing in the central US, and then these reddish colors along the western coast. There are only a few real-time stations that they are currently using for their forecasts in Alaska. There are actually a few more, but there's not a whole lot going on in the northern parts of Alaska. But so hopefully we can agree that we can measure or estimate water vapor, precipitable water vapor using these GPS tools. All right, so moving further down now, we are actually at the surface now, where our signal gets reflected. Alex talked about this a little bit. So we have the direct wavefront arriving at the antenna, and then a reflection of that wavefront coming in to the receiver or the antenna. Okay, so this is what a different schematic of this looks like, right? Direct signal here in blue, then it gets reflected at some planar surface. And this here, this E, that's the excess travel path, right? So the signal takes a little longer. What happens when you have two waves that interact with each other? You get interference, right? You can take a pebble and throw it in a pond and take another one, throw it a little bit farther away. The waves travel outward, and then you get these really cool interference pattern where those two wavefronts are meeting. And that's kind of shown here, right? You can have total destructive interference where you get nothing, or then some kind of constructive or otherwise destructive interference. Okay, so now let's just think a little bit about some of these patterns. So initially, you might have a setup here where you have a GPS antenna, and there's this reflected signal, and the interference pattern looks something like that wave up here. Now we're going to change the environment around the GPS antenna, and we're adding a snow layer, right? So now the antenna height is a little shorter, and what that means is that the frequency of that reflection pattern is going to change. It's going to be lower frequency, longer wavelength. Cool. Now another process or another change to the environment that we could make is we could add plants, right? Over the cycle of a year, plants grow and they get harvested perhaps, right? And what that does is it slows down the signal, and it adds noise, or it lowers the signal strength, so the amplitude gets smaller, as we can see here. And the last one that we can distinguish this way is wet soil, right? So if it rains, the soil becomes wet. That changes the signal some. There's maybe additional penetration that happens into that uppermost layer of the soil. before it gets reflected. And we end up with this very subtle, it's really, in the real signals, it's this very subtle phase shift. Frequency and amplitude remain approximately the same, but there's this little phase shift. Now you can hopefully imagine that, if I can draw these things and we do a little math, we can come up with models that link some property of the GPS signal or these properties of the recorded signal to these physical processes. So for instance, how high the antenna is, or how much water might be in the vegetation, or how wet the soil must be to create these kinds of shifts. And people have done that. There's been work for over more than the last decade on this. Now, one key thing that you have to remember, though, when we do all of this is we're not using the signal that we use for positioning. All we're using is signal strength. So this interference pattern is generated on a signal band that's not dissimilar from the 3 or 4 bars that your phone shows as you get closer or farther away from a radio tower. The antenna measures the signal strength, or the receiver does, and the signal strength changes as these signals interfere with each other. And from that observation, we can infer something about the antenna or the environment around the antenna. Now I'm gonna go through one example where we use these GNSS reflections in southern Alaska, near Homer, Kachemak Bay. There's a GPS station in Peterson Bay that's called P Bay. You can see it as this red dot here. And this is what this looks like. This is at low tide, and this is at high tide, right? So this is what changes the reflecting height, or tide changes the height of the reflector from our antenna. If you haven't seen one yet, by the way, this is tectonic quality, I guess, GNSS monument. Stainless steel rods driven into the stable rock here. And the position is measured at the antenna. This is all epoxied in. These monuments last for decades plus. They're very stable. We can measure millimeter precision with that. You can see some of these along the Richardson Highway, for instance. If you see them, please don't use them for target practice. So now our antenna is up here. This is our reflecting surface, sea level, right? So this is about 7 meters or so of difference. At high tide, the reflector is much closer. Okay? Up there, I'm now showing, at high tide, you can see this kind of long wavelength signal here that one satellite sees, and at low tide, much higher frequency, right? That's what was explained in that schematic before. Okay, now people went ahead and analyzed these kinds of signals throughout first half of April in 2012, and in 15-minute intervals or so, or maybe less, calculated the antenna heights, and these are these blue dots, right, that are showing up all over here. These are sea level height for the first half of April in 2012, inferred from GPS, right? So that's an estimation process. In this magenta line, we have observations of a tide gauge, and that tide gauge actually is in Seldovia over there. So there's a little bit of distance between those two, but overall, I hope, particularly at the scale that we're showing this here, you can agree that there's pretty good agreement between the tide gauge measurement and the GPS. If you do the statistics, you're within a few centimeters of uncertainty. And now, why is that a good idea? Like, why would we want to use GPS that way? Well, you need to know about tide gauges that they are attached to something, and from that something, they measure sea level. This could be a dock or some rock or something. So there are two problems with this. One, in places like Alaska, you have sea ice buildup that can crush these tide gauges routinely during the winter. But also, this stuff all moves, right? So there are many processes that, some of which I showed at the Leatherman image before. There are many processes that result in the crust moving. Earthquakes are one of them. They're very fast. But all the motion of tectonic plates in between earthquakes, right, where you have, some say the Pacific plate coming in and the North American plate sitting here, right, and they don't slide past each other, so there's some strain that's being built up that's resulting in deformation and uplift and inward motion. That's very slow. But any tide gauge that's attached to that rock is going to be lifted up, and so you need to correct for that to get a correct estimate of sea level. Now, if you use GPS, that correction is basically built in. So that's why we are talking about this. A faster motion would be an earthquake. So if you are not familiar with earthquakes, there are a few small ones that I have felt here in the last year even. They happen frequently. And then there are some large ones, like this one here, that's from 2011, March 11th in Japan, the Tohoku-oki earthquake, which was a magnitude 9 earthquake. Those happen much less frequently, right? We've had some larger earthquakes in Alaska. The last magnitude 9 was in 1964. What this shows is a few really cool things. So every blue vector here is the offset of one GPS station during that earthquake. Okay? And you can see the big vectors, right? These big arrows here. There's about 4 meters of motion, right? The epicenter of the earthquake is right about here. So Japan moved 4 meters into the Pacific, okay, during that earthquake. You see, perhaps you can recognize that there's some kind of pattern in here that's actually created by the S wave, right? A body wave that moves through the Earth, and these S wave packets kind of move through the network here. We can visualize that. And then here we can see another type of wave that's a love wave or a surface wave that propagates along the surface once the earthquake energy makes it there. Okay, so now I'm going to show you an animation of this. This is 1 second intervals. The horizontal I just showed you is over here. The vertical is over there. There, the earthquake starts. All the energy is traveling to the land. You can see the buildup of these vectors and kind of that energy of S wave and now surface wave traveling outward. Up here you can see these vectors kind of bouncing around. That's because energy is being trapped in some basin. That's very similar to what happens in the Cook Inlet Basin. Energy is just kind of bouncing back and forth from these walls. And importantly, what I'm showing over here is the vertical, okay? So the scale here, this is a ½ meter. So all the coast near the epicenter went down by about 60 centimeters. Which means that that tide gauge now would be 60 centimeters, or sea level would be 60 centimeters higher, which for an earthquake we can easily correct for. But for the inverse process of that energy all building up, that's much more difficult to correct for. Now, we do have earthquakes in Alaska. I mentioned that already. One of them, the biggest one that we've had recently, happened in July of last year, 21, the magnitude 8.2 Chignik earthquake. Right, so off the Alaska Peninsula here near the Shumagon Islands, we had that megathrust earthquake. And here now the vectors that show horizontal motion are red, right, motion towards the earthquake, or the epicenter for these stations. And then in black we have the vertical motion, and you can see there's subsidence over here at the peninsula, but Chirikov Island actually is outboard of what's the hinge line, and that is actually moving up substantially. Now, we don't just want to be able to say, yes, an earthquake happened and the crust moved by 20, 30 centimeters or something like that. What we are really interested in, or part of my research is interested in, is figuring out what happened at the source. How much did the fault move? And so we can take all these measurements and add a few more from other sensors in, and then make these maps here that show slip of the fault during that earthquake. So this blue rectangle is basically the fault of the Pacific plate and North American plate, right, where they touch and one subducts under the other. That's at a fairly shallow angle, right? You can see the depth contours here from 20 to 40 kilometers. So we take that and we project it to the surface, and that's what this rectangle is. And on that fault now we map the slip that was released during that earthquake. And you can see this is the epicenter of the Chignik earthquake, right? We have 6 meters of slip right here near the epicenter, and then that slip propagated outwards toward Chirikov Island, down to perhaps 1.5 meters or something like that. Okay, so this is important because that tells us which parts of the Alaska megathrust have slipped how much, which we can then use to perform hazard estimates, like which areas might still be slipping, etc. But the other thing that this can be really useful for is actually inform on expected ground motion, but for that we want to perform these kinds of estimates not on weeks to months scale, which this has taken. It took us about 3 or 4 weeks to estimate this from all of the various data. But the question is, can we do that in real time? And that is something that Alex's research is looking into, and he will talk to you about now.
Thanks, Ronnie. Well, let's now dive more into earthquakes. So major earthquakes, so events over 7.5 in magnitude, happen very seldom, but whenever they happen, they create substantial hazard and they are dangerous for our lives. And a good example is pictured in this image showing the damage produced by the largest earthquake ever recorded in North America, the 9.2 magnitude Great Alaska Earthquake from 1964. A more recent example is the 7 magnitude Anchorage earthquake from 2018, which damaged large part of the city, affecting not only its roads, but also civil structures, as you can see from this image. Now, the 2 images that I showed should give you a sense of how damaging earthquakes can be and how harmful they can be for our lives. Now, to mitigate the impact of large earthquakes, cities have started to develop their own earthquake early warning systems by populating earthquake-prone areas with sensors, mainly seismometers, that can capture the faster P waves in order to raise alarms to the population before the slower but more damaging S waves hit. How does this work? Well, it's explained in the same figure. Seismometers collect the data in a network, which is then transferred to an alert center that uses this information to estimate magnitudes for us in real time. If a threshold is exceeded, then the alert center raises an alarm to the population. However, seismometers are known to saturate because they cannot capture the full range of motion produced by large earthquakes. And if you look into this plot, which is related to the 9 magnitude Tohoku earthquake, we actually see that the magnitude estimate based on seismometers saturated at about a value of 8. Now this brings me to my proposal of using GNSS along with seismometers in order to solve this problem. So after considering GNSS along with sensors like seismometers, we can actually characterize not only small but also large earthquake events. And in case of the Tohoku event, we see that after considering GPS, we were able to get a magnitude estimate close to the real one of 9. Now this brings me to a point where I can introduce my research work, which is basically close to exploring and establishing a strategy for using GNSS for earthquake early warning in Alaska. Now, in contrast to the lower 48, Alaska has no operational earthquake early warning system at the moment. From these 2 images, we also see that in Alaska there is a large difference in sensor infrastructure, which is proportional to the amount that we have up here. And this all reflects in a completely different research approach I have to take compared to the one that was successfully implemented in California to the Shake Alert system. However, from the left figure, it is evident that the current GNSS network is sparse and can hardly be used for earthquake early warning. Now, you might wonder why Alaska represents an ideal region to deploy such study. Well, it's mainly because it's located on a major plate subduction zone where the Oceanic Pacific Plate converges under the North American Plate, as it's shown in this inset. And this gives birth to major deep earthquake events, making Alaska a great study region to check if GNSS can be useful for earthquake early warning. Now, furthermore, this map shows all events that happened in Alaska from 1960 onward with a magnitude over 6, showing that Alaska is the state with the most recorded earthquakes in the United States. From all of this, I am aiming to study and use only significant earthquakes, so events that are over 7.5 in magnitude. And unluckily, there were only 4 such events that were recorded from 1990 onward with GNSS receivers, which gives me some data for further exploration. But I think this is not enough in order to make a great decision, and that's why I tried and started exploring simulating large earthquakes with a software called MudPy. By using this software, I was looking at the influence of large earthquakes at locations where we already have GNSS receivers installed, but also at synthetic locations. And in the following, I'll try to play 2 animations to show and highlight the importance of having a strong GNSS network. Before that, I'll try to familiarize you with what you'll see in the animations. So let's start from the upper left corner, where we see that we are situated somewhere in southwest of Alaska. On the map, we have these yellow dots that correspond to current GNSS stations. Then we have this big rectangle, which corresponds to the fault inside the Earth, which was projected on the surface. In it, we have smaller rectangles, which correspond to the amount of slip experienced during the earthquake, with blue regions corresponding to no slip and red regions corresponding to slip of up to 6 meters. Then in the center, we also have an orange star, which corresponds to the hypocenter, so the location where the earthquake originated. And then in the lower left corner, we have like a timekeeper, which shows the amount of time that elapsed from the origination. With time, what you'll see in these videos will be some blue arrows that will increase over time, and then they will also change their orientation, and this corresponds to the surface displacement encountered at those locations and produced by the earthquake. So let's first look into the first case, where we look at the evolution of displacements at current GNSS locations. And this will be simulated for a fake earthquake of a magnitude of 8.2. So what you'll see is that with time, only close by stations will be able to characterize large displacements, while all other stations will not see or experience any deformation or a really small amount. Now, having less stations will have a big impact on our understanding about the source of the earthquake, but also on the rupture scenario in that region. Now, if we consider to populate the entire coast with GNSS stations, we'll be most likely be able to capture a field of displacements and also see the evolution of it. So let's see if this happens. So by playing the video, we see that large displacements show up close to the hypocenter as before, but they are better discriminated than before, having more stations, and they'll start migrating towards the east, getting smaller and smaller. Now this is ideal, since we can learn more about the evolution of the displacement field, and by having more precise data, we'll know more about the hypocenter and when the earthquake happened. Now, I've been looking into this fake information or synthetic data, and in the following I'll try to validate this with real information. And this will give me then the chance to point on locations that are prone to large displacement, to know how to improve the network, but also if we need any software development. And this will all come in a strategy that should consider GNSS for earthquake early warning in Alaska to protect its communities. Now I'll hand it back to Ronnie, which will summarize everything that we talked about so far.
Yeah, thank you, Alex. So I hope tonight you learned a little bit about how the GPS or the global navigation satellite system works, right? There are satellites that are orbiting the Earth. There are multiple constellations. They all beam or broadcast a signal down to the surface of the Earth. Your phones do not need to communicate with the satellite. It's like radio. We all can listen to the signal that comes from these satellites. And they enable, or this system design enables so many applications, some of which we walked through today. First, we talked about the ionosphere and how we can use these signals to learn something about the electron content, maybe monitor even in near real time, space weather effects that are due to solar activity. Further down in the troposphere, we talked about how we can use these GNSS signals and how they're being delayed due to water vapor to estimate how much precipitable water might be in the atmospheric columns above us, and with that aid weather forecast models. Closer to the receiver, I talked about the ability of GPS to solve for dynamic changes in the environment. Here at the example of measuring sea level and resolving tides in whatever time resolution you might want for that. We also talked about snow depth. That's the exact same application, although the time interval in which the antenna changes or the antenna height is much less. And lastly, Alex talked to you about earthquake early warning applications, how we can use GPS to rapidly inform about slip-on faults and perhaps experiment with ground motion forecast applications. And lastly, of course, you can still do this. You can still go to a city and pull out your phone and try to ask for directions if you don't know where to go, or even if you do, sometimes it shows you the faster path. But I do hope that you go away from this lecture and the next time you ask for directions, you take a second and appreciate all the other applications that this technology enables. Thank you.
All right. Thank you, Ronnie and Alex. That was awesome stuff. I came up here 30 years ago from California and have gone through quite a large number of earthquakes myself. So I'm going to kick off the questions here just because that's sort of host prerogative, I think. What I wondered, though, going back to the beginning of the presentation with kind of explaining the satellites and everything, I just wondered, is there an international governing body, or does just each nation do their own thing? How does that work?
Yeah, that's a good question. So, in a sense, each nation does their own thing. There's something that's called the International GNSS Service. It used to be the International GPS Service that kind of unites the science front. There's obviously international governing bodies on the frequency spectra, et cetera, to make sure that those are occupied in a way that the signals don't interfere with each other. But in essence, it is the countries or the European Union conglomerate of countries to their goal to put out a navigation satellite system, right? So GPS was the first one developed by the US Department of Defense. And the initial version of that had some technology that made the signals less useful for civil use, and there were some airline incidents that then resulted in not using that. But the rest of the world sees that commodity or that great utility that is in the hands of the US military, so you don't know whether you'll continue to be able to do that. So the Europeans, for instance, then started developing the Galileo system, which at its core was supposed to be a non-military satellite system that would focus on civil use. So there are multiple pathways to get to your own navigation satellite system.
All right, got a couple of questions from viewers here. All right, so we'll start now. Here's one from Victoria Rigo. Victoria asks, what kind of lead time would a GNSS early warning system provide, and would this early alert allow any effective preventive measures?
All right.
So I don't know who wants to take that one. You guys fight that out.
Alex, do you want to, or should I?
I can try. Yeah, basically I can try give an answer based on literature review I did, and I think it's many couple of seconds to tens of seconds from what I've read. So it really depends on the network structure and on if they are actually effective. I think Ronnie showed through his research in California and the shake alert, basically, the data comes in and they get a warning when the earthquake happens, and with information about the magnitude and the location where it happened. So I don't think there's more than that, but I think Ronnie can give more detail on this.
Yeah, thanks, Alex. So, it depends on a lot of factors, as Alex has just alluded to a little bit, like how shallow is your earthquake, how close are you to the earthquake. So for instance, if you have a large earthquake somewhere out in the Aleutian and you care about what is happening, how much warning time you have in Anchorage, you can have minutes of warning time, right? So even a geodetic system, which is much less sensitive, so it doesn't detect the P wave, which the seismometer is working on. It detects the actual large ground motion. So, in a sense, you already lose some time doing that. But even in that case, you can still come up with scenarios that are really realistic for a place like Alaska, where that time difference is still not very consequential in the warning time. And the Inniskin earthquake of 2016 that was in Cook Inlet, it was a very deep event. That is one example where we actually experimented with that quite successfully and could come up with a GNSS and seismic-based magnitude before the S waves made it across Cook Inlet.
I had another question here, and it has to do with the GPS itself and accuracy. What sort of things affect accuracy, and does the device itself affect accuracy? I've got my iPhone, but I also have a Garmin. So maybe you can tell us a little bit about that.
Alex?
Yeah, I can try to give an answer to this. So there are lots of factors that influence your accuracy. Let's start again from the space. Basically, each interaction with these layers, with the ionosphere and troposphere, has an influence on your accuracy. Then the quality of your antenna at ground, so that's going back to you, Rod, gives a huge influence on your accuracy. So if you have a low cost antenna, you can end up with meter accuracy. But if you have a great geodetic antenna, you end up with millimeter level precision, or say centimeter level precision. There's also how you install the receiver. So if you have surrounding obstacles around, that also bounce the signal. Then there's also how much data comes in. So with more data, so more frequencies, you get a more precise coordinate. So yeah, I think there are lots of things that can influence your accuracy in the end.
Okay, let's do another question here from a viewer. Ron Inouye asks, is there comparable research going on elsewhere?
So, before I after I finished my PhD here and before I came back, I spent some time in the Bay Area and worked on developing a prototype that integrates high-rate GNSS into an existing seismic earthquake early warning system. There are a few groups along the West Coast working on that, and in Japan and in other places that have large earthquakes. There is, as far as I know, no place that uses these the geodetic data actually in an operational sense. So even though along the West Coast there's no shake alert, which is sending out earthquake early warnings to civil people, to the population, in addition to industry subscribers, etc. That doesn't use GNSS yet. So, so yes, there are other groups working on it. One of the great differences in Alaska, though, is something that Alex talked about a little bit, is that it's huge and it has very clustered infrastructure and population centers, right? So the kind of shotgun approach of deploying sensors all over Alaska is potentially not the best way forward. There's maybe a lot to be gained by thinking creatively about what a strategy really should be, and part of that is what Alex's work is going to be contributing to, moving away from perhaps some of the paradigm that is being used elsewhere.
I wondered with Alex's research, and this is maybe this is a reach, I don't know, but are there other potential uses for whatever he comes up with here?
Alex?
Rod, can you please repeat your question? I couldn't hear the last part. Sorry for that.
Alex, I wondered if there are other potential uses for the research you're doing.
Well, I'm mainly looking into how to use GNSS for earthquake early warning. So that's actually what I'm looking at. But I think like out of it, we can derive more information about sleep models and earthquakes, or we could even basically get more information about locations that nobody knew before that they can get displaced or not by earthquakes through these synthetic simulations. So I was not thinking entirely like how can my research like deviate from what I'm planning to do, but I think it's centered around earthquake science. So yeah, that's also the beauty of doing research, because you don't know where you can end up with it. So yeah.
Yeah, and some of the infrastructure structure that is being developed around it, and some of the things we learn is going to be transferable to other hazard early warning type things, landslides or volcanoes, obviously at much smaller scale, and again, using different strategies. But overall, if you think about the engineering aspect of getting data from the field fast enough to deal with earthquakes, you can deal with slower hazards like volcanoes or perhaps a landslide in a similar fashion, but you have to factor in the much smaller spatial scale that you're dealing with.
All right, let's go to some other viewer questions here. Doug Loschbaugh, he has two questions, all right? So we'll do one of them to begin with and then get to the other. Doug asks, do the satellites travel fast enough to distort time measurements, and how do you synchronize their clocks?
I think I can try. Yeah, I can try doing this. So it's not about how fast they travel. So mainly the time information can be distorted either naturally through the atmospheric layers or synthetically by someone through spoofing. But let's take into account that nobody's spoofing and messing up the signal. So in case that this is distorted, the synchronization happens actually at the receiver level only for the clock drift. So the receiver clock drift, and that's basically through a mathematical process where we estimate the drift, and there you have a correction for that.
So yeah, that's how you actually correct for the drift of your receiver.
Yeah, and there is a, the controls segment that we didn't really talk much about. But there's this whole aspect of say, let's focus on GPS. There's distributed stations over the globe that stay in touch and actually send signals to those satellites that can control the orbit, etc. They also keep an eye on the clocks. So all these satellites have atomic clocks, which are highly precise. But we have a means. If you know exactly where your position is, you can estimate other parameters, say clock drift of a satellite or something like that. So there's an entire segment of the Department of Defense, or now Space Force, that actually keeps an eye on the health of these satellites, replenishes them, and makes sure that these signals are accurate to achieve the position precision. One thing, if you do these estimates, that you have to take care of is, of course, that the satellite sends its signal and it keeps moving. So there's this whole aspect of you're dealing with signals that from a platform that you consider stationary, that's actually moving as it's producing the signals. But since we have very good control of the orbits of the satellites, this can all be corrected for.
All right, let's go to Doug's second question. Wait, now Doug has a third question. All right, we'll just do his second question here for now. Which system gives the best coverage of Alaska? GPS, Galileo, Russian, or Chinese satellites?
Alex?
Yeah, I would say it's GPS, but I'm not sure on this, so please correct me.
Yeah, so GPS and GLONASS are the two constellations that are complete. Galileo is still missing a few satellites from achieving complete constellation, and complete constellation means that it can operate on its own. I can tell you that in many science applications in North America, we are very slow to transition from GPS only to multi-GNSS. That's something, there are various reasons for that, but it's in the process now. So for science applications, there's a lot where we're using purely GPS, and we're starting to phase in other satellite constellations now. Because they provide more piercing points or general better position control.
Doug had a follow-up to his first question, and then we're going to get on to questions from Nicholas and Victoria. Doug wanted to know, could this approach be used to detect and gather data on subsurface nuclear testing?
Okay, this one is on you, Ronnie.
Well, if you're close enough to the nuclear test that it changes the position of points on the Earth's surface, you can measure that, right? Like if you have a subsurface explosion and it either dynamically creates waves that are large enough to shake the ground similar to an earthquake, or permanently move the surface, we can measure it. So if it's on the order of a few millimeters to centimeters, it's not the standard technique. It's a lot easier to use seismometers or infrasound sensors for those kinds of things because of the sensitivity, and you want to be able to sense a nuclear test with sensors that are maybe globally distributed that is happening in, say, North Korea or something like that. And you will not have access to ground scientific grade GPS or GNSS streams, station streams in places like that. Because there are a lot of places where highly precise positions are still state secrets.
All right. Here's a question from Nicholas Hassan. And Nicholas asks, does GNSS clearly see ionospheric disturbances during earthquakes? Given the large slip displacement for earthquakes, up to 6 meters, I think that's what he's got there, could a GNSS early warning system be developed for monitoring ionospheric slips or dips above?
Yes.
Okay, next
So
question.
I could just stop there, but there are a bunch of really cool papers, including animations, but the animations are kind of, they're a little spaced out because, everything's moving around with the satellites. But yes, there are, for large earthquakes, we do see disturbances in the ionosphere. For large volcanic eruptions, we can measure that using GPS as the shock wave is arriving. And we can also track tsunamis as they are propagating across the Pacific in the ionosphere as we disturb it due to gravitational waves.
Victoria is back with another question or two here, it looks like. Victoria asks, can you describe the process involved with a sensor network that would be part of a GNSS system? Does it need to have several on-ground sensors in remote locations, or can a lot of info be gained from modeling? What would it look like in practical terms?
Alex, you want to go ahead?
I'm not sure what Victoria means with a sensor network that is part of a GNSS system, but I assume it's all about the receivers at ground. So, and yeah, modeling, it really depends on what you're looking at. If you look at specifically at displacements, so to track the movement of the ground, I would say that the more sensors, the better. So just use the observations. But if you go for modeling, you make lots of assumptions. So, but this is my personal,
I can maybe add something to how I understand this question. So with like the whole point of what Alex talked about, the simulation, is maybe get an idea of what a sensor network that follows certain assumptions could look like, how dense, say, a network would need to be if we wanted to reliably, within a certain amount of time, figure out what the slip distribution for magnitude 8 earthquakes in Alaska is, or something like that, right? If you actually do want an early warning system, be it just seismically based or seismic and GNSS, you need a lot of stations actually on the ground. You have a lot of engineering requirements towards them. You want them to telemeter data in near real time, so you need some kind of communication system. Potentially, if you do earthquake processes, shooting something to a communication satellite using satellite link and receiving it back is probably introducing too much of a delay. So you need some kind of radio link system that needs some redundancy because it can fail. It needs to have the required uptime. In places like Alaska, obviously you have pretty harsh winters, and if you move out into the Aleutians, right, you have other harsh weather conditions. So you have extreme requirements towards your power systems. There isn't just a wall outlet that you can plug these things in. You need batteries, solar panels, wind generators, etc., to make sure that the instruments are going to be running. So there's a simulation aspect where we're kind of trying to figure out what a system could look like if we make certain assumptions, and then there's the reality of like what would actually be required to have on the ground to make this thing work from an engineering perspective.
Before we get to Victoria's second question, I want to tell viewers that we do have time for a couple more questions, and I know we've got a couple here. Victoria asks, would any of the low Earth orbit satellite arrays that are hot in the news of late interfere or be problematic with the current GPS satellites?
Alex, should I take that, or do you want to?
Well, I assume not, because all these constellations are fairly precisely designed before they are launched. So
Yeah, and they operate in different frequency bands, right? So it would not happen if there was substantial interference. Though that is not to say that that is always the case. There are sometimes discussions where some communications industries want to offer certain services in a frequency band that's very close to the, say, GPS band, and you would then suffer from substantial interference. So there's authorities that try to keep an eye on that to ensure continuity of these services.
And also, I think there's much more cooperation in space.
Gail asks, does type and depth of earthquake affect accuracy? It seems most really big quakes are in subduction zones and are deep compared to the San Andreas Fault in California. Both are near population centers. Which is likely to give us the best warning time?
Well, there are a few things to unpack here. So yes, if you have shallow earthquakes, say along the San Andreas Fault, you can put your sensors very close to it, so you can have a very dense array. And dense, as Alex has been pointing out, helps us with resolution. Now the question is what it is that you want. Do you want to know very precisely what the slip distribution of the fault is? You want very dense distribution. Do you want to know, but close and far away, right? Because if you have all your sensors very close, right on top of the fault, you can't see very deep. So you want some sensors also a little bit a ways away. If you have subduction zone events, right, it's absolutely true. You're much farther away from the event. You could see that in the Japan animation. That the earthquake happened, we started counting up the clock, but the vectors on land weren't really moving yet because the energy actually needed to travel through the earth and make it to the sensors. So you are at some form of disadvantage because you are farther away, but that also helps because it removes some of the energy already, and it separates the P wave and the S wave some. Actually reducing some of the shadow zone if you are far away. Now then, with subduction zones, the problem too is the geometry comes into play. They're usually dipping some. So if your earthquake starts very shallow, far away out at the what we call the trench, that distance may be farther away than a deep earthquake, which could be directly 40 kilometers below. So if you do that geometry, a shallow subduction zone earthquake out by the trench might actually not be more desirable from the warning perspective. I'm going to come back to that. From the warning perspective than say a deep event because it's closer to you. Now you don't want shallow subduction zone events because you have the whole tsunami story that comes in there, right? The more the seafloor gets displaced, the more you create that secondary hazard. But I hope that answer helped a little bit understanding that.
All right, I'm going to ask a question here. I'd like to know, in the area of early earthquake warning as an area of research, how active is that area of research, and are we making good progress, and what's the end goal we're trying to achieve? How much warning are we trying to get?
Do you want to take a shot first, Alex?
Yeah. So I think I pinpointed a few times. We are at the stage, an incipient stage of exploration, but there are examples of success in California. And I think in the end, it's not only about we, the scientists, how we do the research, but also how much impact we can do that at the authority level. So the end goal, I mean, if it will be about me, I would like to implement this the next year, but I think we have to stay close to the ground and do the research, output some solutions, and then if people like them, then move that to the engineering part and implement it.
Mm-hmm. Yeah, so Alex's answer is very much for the Alaska case. That's what he's focusing on. In terms of how active is the research, it's actually interesting if you look at the literature. Like that goal of earthquake early warning has been around for a long time, right? Like that's always the thing. It's like we know that P waves travel faster than S waves. S waves bring the shaking. We better be able to tell people that the S wave is coming. There are some papers that were written in the 80s that kind of started coming up with these computerized real-time systems. But the technology lagged behind, and the ability to have kind of the dense sensor networks. And something that now is 11 years in the past, but very much part of my active research career, was the Tohoku earthquake. And within the US, it really spurred the research, and globally, because all of a sudden we had a rich data set of a magnitude 9 earthquake that we could study from all angles and have the use case of, look, the Japanese had an earthquake early warning system running at the time that was fully deployed. They did in real time estimate that magnitude. It was a magnitude 7.9 or something like that. It was too small for the actual event, which we often use, and I do that all the time. I made similar slides before as like, look, the early warning system didn't work all that well because they didn't get the magnitude right. But they did send out a warning. A lot of people in Japan received a warning well before the shaking arrived. And what we can add on is, and have worked on since that event, is finding ways to get better at assessing these large magnitude events, which need these multi-sensor approaches. So, it really depends on, to fully answer the question, it depends on where you go. In California, Washington, and Oregon, it's a very active field of research and application. There is now a public system that is there. In Alaska, we are, as Alex says, kind of at the incipient stage of figuring out how we can, what strategies we really should follow to implement something like this, because we have this huge state to tackle somehow, right? And it's going to take many different agencies to come together and realize an actual on-the-ground live earthquake early warning system in places like Alaska that are fairly remote to do that. We need lots of many people at the table.
Victoria is slipping in one more question here, and then I think I'm going to ask the last question unless another one or two come in from viewers. Victoria says, does any of the early warning data feed into predictive models successfully?
Predictive models?
I think it's about sleep models.
I'm just the question reader.
Oh, okay. Slip models?
In real time.
Does any of the early warning data feed into predictive models successfully?
Okay. So I want to tackle one term in there, and then I'm going to hand it to Alex, which is that of prediction, right? It's a very slippery slope. We don't want to get into earthquake prediction. So all that early warning that we are dealing with is an earthquake happens, it's underway, and we're picking it up before the actual shaking arrives, right? So there isn't really prediction of an earthquake. There's maybe, and now we're getting into splitting hairs perhaps, forecasting of ground motion or something like that, right? But I'm bringing that up because the field of earthquake prediction was another one of those dreams in the big field of seismology. It's like, well, we know where the faults are, the big ones. Can we actually predict when and where an earthquake is happening? And that has been so far, unfortunately, unsuccessful. We weren't able to pinpoint those. So that's about the term. Alex, do you want to add anything to the answer specifically?
Not really. I don't know if she pointed towards magnitude estimation. So what earthquake early warning does is mainly using information and to give us a magnitude estimate, and that will be updated with time. And in the ideal case, will be warned before the S wave hits our location. So
Yeah. And yeah, we had a demonstration system running using both seismic and geodetic data during a magnitude 6 earthquake in California, the Napa earthquake of 2012. And we were able to make these colorful maps with a delay of a few seconds. So it ran. The warnings weren't going anywhere because it was a testing research system, but you can make that happen with the infrastructure.
Okay, last question, and this is for both of you, all right? I would like to know what, for each of you, what is your earliest recollection of being in an earthquake? Either as a child, either that, or what is your most striking recollection of being in an earthquake?
Alex?
yeah, I don't have so much experience with earthquakes, even though some happen in Romania. So I only remember one, which basically woke me up. And I think I already felt two in Fairbanks this half a year. So I think there's time to catch up with that.
Yeah. My answer to that is, I felt the occasional small earthquake. I think the first one I felt was a small earthquake in Iceland, which had one of those cool old helicorder setups where there's a spinning drum and this little arm that from the movies, kind of shaking back and forth. It was on display, and everybody ran in the building to that thing to see how large it was. But really, what struck me and got me into earthquake science and early warning was the Tohoku earthquake. I woke up in my cabin in Fairbanks in 2011. I think it was a Saturday or a Sunday. I might be wrong about that. I know that I went skiing that day because I was sitting on the chairlift at Skiland and thinking about that earthquake. Like, you get an alarm on your email or whatever. It's like there was a magnitude 9 earthquake in Japan, and you just know that it's huge and disastrous. And there's going to be a tsunami, and it's like, it's crazy. And I started looking at some of these data products, and I made variants of these animations that people found interesting, and visualized for my first time the seismic wave field. So one of those frames came out as I produced it, as a grad student sometime late at night, and I had it on my screen. I was like, oh, I can see the wave field, and ran to a fellow grad student. So it's not the direct experience of a large earthquake, but actually working on the data and making figures that you've created for the first time, visualizing data in some way that nobody has seen that way yet. So that was certainly my hook into that field.
Ronni and Alex, thank you so much for the insightful presentation. I know that I will never look at my GPS device the same again, all right? And I will treat it very carefully, all right? Thank you very much.